Today, I will talk about the modulation of spin-orbit interaction by a gate voltage. This effect is called the voltage-controlled magnetic anisotropy, or VCMA in short. The VCMA effect describes the fact that in a capacitor in which one of electrodes is made of thin ferromagnetic metal, the magnetic properties of ferromagnetic metal changes when voltage is applied to the capacitor. The VCMA is a puzzling and even surprising effect. It is unclear how and why a gate voltage influences the magnetic properties of nanomagnet, because the gate voltage is applied only to boundary of the nanomagnet but not to the bulk of the nanomagnet. The nanomagnet is made of ferromagnetic metal. Inside a metal, the electrical field is screened by free electrons and cannot penetrate deep inside the metal. As a result, the voltage which is applied to the gate may penetrate into and affect only the few uppermost atomic layers of the metal near the gate. However, the change of magnetic properties of the uppermost layer by the gate voltage affects the magnetic properties of whole nanomagnet. Till present, the physical origin of the VCMA effect is unknown. There are many suggestions, which include both realistic suggestions on possible origin and unrealistic ones. For example, there is a suggestion that the Raspberry effect is a VCMA origin. This suggestion is definitely incorrect because a substantial Raspberry effect may only exist at temperature below 1 Kelvin, but VCMA effect is a room temperature effect. The most reasonable explanation of the VCMA effect is that the strength of perpendicular magnetic anisotropy, or PMA in short, is modulated by the gate voltage. It is known that the orbital deformation of uppermost layer of the nanomagnet creates a very strong spin-orbit interaction in one uppermost layer. It could be order of magnitude larger than spin-orbit interaction in the bulk of the nanomagnet. As a result, the magnetic properties of whole nanomagnet is determined mainly by the magnetic properties of the uppermost layer, which is with only little influence of the bulk of the nanomagnet. In this case, it becomes more understandable why the gate voltage, which is applied only to the uppermost layer, affects substantially magnetic properties of whole nanomagnet. Still, the specific of how the gate voltage changes the magnetic properties of uppermost layers is unclear. There are two possible realistic explanations. The first explanation is that the gate voltage modulates the Fermi level at the ferromagnetic metal gate boundary, which changes the filling level of spin-up and spin-down localized electrons. Under gate voltage, a charge is accumulated and therefore the number of conduction electrons increases. It leads to an increase of the Fermi level, and as a result, an increase of the number of localized d electrons. The spin-up band is radialmost filled, thus there are not so many unoccupied states available in this band, and the increase of the number of spin-up electrons is very small. In contrast, the spin-down band is nearly empty. There are many unoccupied states available in this band, and the increase of spin-down electrons is large. In total, the difference between spin-up and spin-down electrons becomes smaller, and the total spin or magnetization at interface decreases. It reduces the PMA strains. The second suggested mechanism for PMA modulation by gate voltage is orbital deformation. When a gate voltage is applied to the atoms of the uppermost layer, the orbitals are deformed. The orbital is shifted along the applied electrical field so that the center of the orbital is shifted from the position of the nucleus. As a result, the electrical dipole of the orbital increases, but more importantly, the orbital shift substantially enhances the strength of spin-orbit interaction. For example, magnetic field of spin-orbit interaction may increase several times. In this work, the strength of spin-orbit interaction was measured as function of gate voltage in an uncoupled nanomagnet. For this purpose, the whole measurement setup was used. Both bias and gate voltages were applied simultaneously. The whole voltage was used to measure magnetization tilting angle on the externally applied magnetic field. A high-quality MZO gate was fabricated using several steps of gross interruption and anneal. The gate can withstand the gate voltage of 3 V without any measurable leak. All details of experimental setup can be found in this video. The details on how to measure the strength of spin-orbit interaction are explained in this YouTube video. In short, we have applied biased magnetic field along the magnetic z-axis. Additionally, we apply and scan another magnetic field perpendicular to the z-axis in order to measure an anisotropy field. The perpendicular magnetic field tilts the magnetization. The field which is required to turn the magnetization fully in plane is called anisotropy field. The larger internal or external magnetic field is, the larger anisotropy field becomes. Anisotropy field is linearly proportional to applied external magnetic field, and proportionality coefficient is coefficient of spin-orbit interaction. Coefficient of spin-orbit interaction is evaluated from measurement of this linear dependence. This is measured data of anisotropy field versus external magnetic field. Lines of different color correspond to a measurement at different gate voltage. As you can see from this formula, a plot of difference between anisotropy field and external magnetic field is more informative. The dependence on gate voltage is substantial. The slope of all lines is negative, means that coefficient of spin-orbit interaction is always negative. It is very common for this type of nanomagnet. You can see that even in absence of external magnetic field, anisotropy field depends on gate voltage. It decreases as gate voltage increases. Additionally, the slope of lines depends on the gate voltage. Due to different slopes, the gap between lines decreases at larger field. This graph shows the measured anisotropy field and coefficient of spin-orbit interaction as function of the gate voltage. You can see the dependencies are opposite. Anisotropy field is largest at negative gate voltage, and coefficient of spin-orbit interaction is largest at positive gate voltage. This dependence is surprising but systematic. This slide shows statistics for a measurement of different nanomagnets. This graph shows a measured change of anisotropy field and coefficient of spin-orbit interaction when 1 volt of gate voltage is applied, versus measured anisotropy field of the nanomagnet. Each dot corresponds to a measurement of individual nanomagnet fabricated at different parts of the same wafer. Even so, there is a variation of voltage dependence from nanomagnet to nanomagnet. The change of anisotropy field is always negative, and change of coefficient of spin-orbit interaction is always positive. It is very surprising result that the gate voltage dependencies of anisotropy field and coefficient of spin-orbit interaction are opposite, because anisotropy field is linearly proportional to coefficient of spin-orbit interaction, and therefore a change of anisotropy field should be of the same polarity and be proportional to the change of coefficient of spin-orbit interaction. As you can see, the linear dependence of anisotropy field on the external magnetic field, which we measure, can be represented as a product of coefficient of spin-orbit interaction and sum of external and internal magnetic fields. This undoubtedly proves that anisotropy field is linearly proportional to coefficient of spin-orbit interaction. Then, how it is possible that polarity of the dependencies on gate voltage are opposite? The reason for the opposite dependencies is the existence of another parameter which depends on the gate voltage and which influences anisotropy field. It's a demagnetization field. The modulation of anisotropy field due to the modulation of demagnetization field is known, and it is strong in multi-layer nanomagnet. Details about this fact are explained in this video. If increase of coefficient of spin-orbit interaction causes a proportional increase of anisotropy field, the dependency on demagnetization field is opposite. An increase of demagnetization field reduces the anisotropy field. Our observed opposite dependencies on gate voltage can be well explained when both coefficient of spin-orbit interaction and demagnetization field increase when the gate voltage increases. At the end of this presentation, I would like to make a note about the possibility of magnetization reversal by a gate voltage. As you can see, a change of anisotropy field under 1 volt of gate voltage is not very small, but is still only 4% from the total value of anisotropy field. Therefore, such a small change will not lead to the magnetization reversal, at least to a direct magnetization reversal. However, this small gate voltage induced change of anisotropy field is sufficient to make a parametric magnetization reversal. The mechanism of parametric magnetization reversal is similar to the mechanism on how to make a large amplitude of swinging using quick pushes. This video explains all details about parametric magnetization reversal. Only I would like to emphasize that the parametric reversal by a gate voltage requires that there should be a magnetoresistance in sample, and there should be a bias in plane magnetic field. Otherwise, there will be no gate voltage-induced magnetization reversal. In conclusion, gate voltage dependencies of strength of spin-orbit interaction and anisotropy field are measured and found to be opposite. It is because both demagnetization magnetic field and coefficient of spin-orbit interaction simultaneously increase with an increase of gate voltage. The gate voltage dependence of demagnetization field dominates over the gate voltage dependence of coefficient of spin-orbit interaction. As a result, the gate voltage dependence of many magnetic properties of iron-cobalt-boron nanomagnet are following the gate voltage dependence of demagnetization field, but not the gate voltage dependence of spin-orbit interaction.